Hello, this is a short video demonstration of the real vibration shaker controller. The controller can be connected to any type of vibration shaker, whether it be electrodynamic or servo hydraulic, and also our system can control any number of axes simultaneously. This system here has been set up to control up to 3 axes, or degrees of freedom as we call it, and as you can see in the middle of the screen here, they've been labeled as vertical, or known as heave, pitch or roll. So the first thing to do is to decide which degree of freedom to activate. So in the first instance I will simply assume that we have a single degree of freedom vertical vibration shaker. So I will activate the first degree of freedom and I will set the correct parameters for the shaker. And this is done using the SDoF setup tab on the menu. The user can change the label, so I can change that to heave, for instance. I will set the units. I can set the units of a feedback sensor. In this case it's an accelerometer. We set the unit of a feedback sensor, which is very important. If the feedback sensor has a DC response, we can remove or not the offset or the DC value. We can change the gain of the ADC, the analog to digital converter. In this case we leave it to 10. We can filter the signal. We can apply various digital filters onto the feedback signal if necessary, and a few other parameters which I won't go through here. I will go through later. And here I will enable the degree of freedom system, and you can see it's been changed to heave. To undertake a normal stationary or constant RMS vibration test, we need to select the target spectrum, or PSD. So here we have a whole lot of PSDs which we've already pre-programmed, which are available. So we can choose, I think in this case was a ISTA steel spring. We can choose for an STM spring, and you will see the PSD on the top right curve is shown here. So I'll go back to say the ISTA steel spring. And here we're going to produce a stationary test, so we're not going to produce a test with fluctuating RMS. So we select an RMS distribution sheet which is stationary, and we can change the RMS level. Here I've chosen a 4 meters per second squared, or 0.4 G roughly, stationary RMS, and that's all I need to do. So I can then I change the test duration to say 1 hour. So I'll type 60 minutes, so that shows 1 hour. Start the test. It calculates the displacement required. In this case it's 37 millimeters. That's well within the shaker's ability or capabilities. So we'll proceed. It will now, the system will now proceed in synthesizing or creating a random signal 1 hour long in accordance to this PSD. We've already set up the shaker, so we know the shaker identification, or the system dynamic or transfer function, if you like. We've already measured that, so we're going to use that. That doesn't need to be measured very often. It takes a little while to generate the signal and compensate it for the system transfer function. The vibration shaker controller effectively works as a follower, so it does a lot of initial work into pre-compensating the signal to get a fairly accurate representation. Okay, it's now completed, and all we need to do is make sure that all the connections to the vibration shaker are correct, and then we simply start the controller. And immediately we see a reaction to the signal. So top left is a little scope that shows you the feedback signal, which is the acceleration levels achieved on the vibration table. Top right, which I can zoom this, is the actual target PSD and also the achieved or the reproduced PSD. As you can see here, the dark blue line is what we measure. That's the average PSD. And we can move that little box here, and all the information is given here. Bottom left is simply the RMS level, so that little white yellow diamond gives you an idea of how long there is to go. So essentially it's a time thing as well. But this graph here is useful for synthesizing non-stationary vibrations. And on bottom right is the probability distribution function of the synthesized vibration, compared in this case with a Gaussian signal, and we also compute the kurtosis, which is a good indicator of how Gaussian the signal is. And that's it. So then the test can be carried out for the duration. We can of course pause it. We can pause the test if we wish to inspect the sample, do some resetting of the sample, and then we can resume the testing, and the clock will keep a tab on where we are. And that's basically it. This is essentially the way ordinary random vibration controllers work. So I shall complete this video here, so we can stop the test and we can print the data, print the graph to be included in some report. If you need more information, please visit our webpage, realvibrations.com.